talk of this morning. The speaker is Ilaria Rossinelli from Lausanne, who will speak about Motivic classes of curvilinear Hilbert.
Thank you, and thank you very much to the organizer for inviting me here to speak, and also for organizing this workshop that has been an incredible research opportunity. I am indeed going to tell you about Motivic classes of curvilinear schemes, and I think a good reason that I could give you to be interested in these objects that you will see how hopefully fit in the workshops GLT and enumerative thematic is that. Okay, let's some setting. So we fix A will always be an algebraic. Is it big enough?
Make it a little bigger.
Thank you. With an algebraically closed field of characteristic 0, and we will always consider some z, some variety over k, in x a smooth ambient variety, and some point that we are interested in studying. When we consider z, and the curvilinear open in its punctual Hilbert scheme has actually been proved by Ecole to correspond to some non-reductive JT quotient. So non-reductive JT. This will be my notation for the open. Some k of z. This is the punctual part. Corresponds to, in particular, the quotients of k jets of holomorphic maps on z, our variety, by the smooth reparametrization action, the reparametrization of the origin. So k is the regular basically of A1. So we have this quotient, this JT quotient. We're interested in studying it. It studies its geometry. Because, for example, the curvilinear open appears in actually a lot of problems, a lot of questions, as we can see, for example, in the list that Joachim gave us. And in the singular case, when Z is singular, it is even more mysterious. We know even less about its geometry. And to study it, for example, we can consider its Motivic class.
Do you have a dimension in mind for Z?
Yeah, I will later fix it for Z. No, we can say what will matter is just the dimension of X, of the ambient to consider.
Oh, Z is 0 dimensions.
No, that is any closed in Z, any subvariety.
Some variety. Could be singular.
It will be singular, to say something interesting. So if we consider its Motivic class, really as an element of the growth and differing of varieties, why should we consider this? This is very different, probably from the techniques we've seen during the rest of the workshop. But this is still an interesting object to study its geometry. For example, in the case of plane curves, there is a very interesting conjecture that was proposed by Oblomkov, Rasmussen, and Schende, where, let's say, roughly they try to give a topological interpretation to the Motivic classes of the full Hilbert scheme, not just the curvilinear part, but still it is worth to consider this type of object. And how will we study these Motivic classes? We will actually make use of another quite mysterious object that appears in a singularity theory, but of a different flavor, which are Igusa zeta functions. I don't want to tell you much about them. It's just an object that appears in a different area of singularity theory. For example, it lies at the heart of the monatomy conjecture that was indeed proposed by Igusa. Let's say it's about some arithmetic and topological aspects of that. Okay. So we have all these objects. We started with the curvilinear open, so some sort of GIT quotient. We consider its Motivic class, and we want to study it using Igusa zeta functions. How do we connect all these different objects? Because we would like to use them jointly to use one to say something about the other, and maybe the other way around. Concretely, what we will do is relate the Motivic measure that was introduced by Kontsevich and later further developed by Denef and Lausanne. Relate the Motivic measure, mu, that we can put on the arc scheme of the ambient variety. This is the only place where n will come into play on X infinite, the arc scheme of X, related to these classes. Okay. So this is the setting, more or less, where we are. If there are no questions here, yeah?
So could you just remind me of the definition of this curvilinear?
All of them. I will do all of them now. Yeah, this is just the intro.
Okay.
Okay, we start with curvilinear schemes instead of Motivic integration, because indeed we need a lot of background. Okay. We will always work with punctual Hilbert schemes, even if I don't say punctual anymore. In particular, let's just say. The punctual schemes is just, the subschemes that are supported just at the point we are interested in. And in here we can take the curvilinear part, which this is an algebraic definition. No, sorry, this is Hilbert is where we learn. This is Hilbert such that we ask for to its ring to be isomorphic as a K-algebra to this type of rings, this truncated power series. So this
Zero is just one.
Yeah, it's just a point that we are interested in studying. At some point, it will be a singularity, a singular point. But for now, we fix a point just because we work with punctual schemes.
Scheme structure on this, or are you taking the reduced structure?
Here, we take that one, the quotient structure that you get from there.
Okay.
Just do that. Okay. Other questions? Just the Hilbert schemes part. And this is actually it. Because we need more background actually in Motivic. In Motivic integration. Okay. So I told you we have a measure where we use a zeta function that will be some sort of integrals. But before that, we need a measure space. And to construct it, first of all, we need jet schemes. So, again, for any K, okay. Okay. So, everything that I do here, of course, can be done for X as well, but we do it for Z for now. It's just defined as a scheme representing as a certain functor. Xk representing
Zk.
Thank you. Yes. Yeah. Yes. Okay. I mean, this is just a definition. Consider this type of morphisms. The important thing to take from this definition is the following, which is that the K-points of these jet schemes corresponds to the, I mean, if you plug in K here, okay, it's just, is the KT K-points of the variety we start with. Okay, so these are our building blocks that we use to construct our measure space, that is the arc scheme. This is I'm simplifying a bit the definition, but we can define as a limit of these guys. So there's the and as a limit, it exists. One, of course, needs to check everything I'm saying here, but just take it as definitions. Are there any questions here?
Sorry,
Yeah?
it's a question actually. So you mentioned this ORS, but that is, in the planar singularity case, that's for the entire Hilbert scheme, not
Yeah.
just the curvilinear. Okay.
Yes. Yeah. It's that the ORS part, if you want, is just a motivation to consider Motivic classes rather than some other type of, invariant or enumerative technique. The curvilinears were a starting point to then say something eventually about the rest of the Hilbert scheme, but that is in progress, will not appear here. Okay. And also here, the important thing to take home from this definition is actually the same. That the K-points of this scheme are the points now in formal power series of the variety we start with. Together with these schemes, we also have some interesting maps. In particular, I'm interested in the truncation maps that we have from the arc scheme. That is, it is in formal power series. If we somehow if we truncate these points, we get a correspondent map. You can also think of these maps as the natural projections that come with the limit definition. Okay. So now we have a definition for the arc scheme, and this is actually if one wants to study the singularities of Z, which is what we will later do. This per se is already actually very interesting and nice object to study per se. There is a lot of work on that by Borghese, Murtada, Mustaza, and require a lot of people working on this. But we will not use it this way. We are not interested in the scheme structure of Z, but we want to use it as a measure space. So because indeed Savage and later the Neff and Lausanne equipped it with a measure. So if we want to discuss measures, we need to discuss measurable sets, and we need to start with the definition of that. So we say a subset of the, here I do it, on the ambient. Because to say something about about Z, we will see how it behaves in the measure of the big ambient space where we are. Okay, so subset here. We say that it's measurable when actually it is a pre-image of something that comes from jets. Some unions of Z is locally closed. We take the pre-image. We say that this kind of sets are measurable. And for these, the measure is defined as a certain limit. Choice. Okay. This one. That takes value where we have the Grothendieck ring that we start with. Here first of all we need to invert the L, the Motivic class of the line. And here, okay, we have this sequence, we have a limit, we would like this limit to converge somewhere. So for this sequence to be a certain Cauchy sequence, we need a certain completion. So it's a completion with respect to the following filtration. Now we can say where this limit lives. Just K0 varies too little. Okay. So of course this is just some sets, but this measure one can prove that it can be really extended to a sigma DT measure, to the full Boolean algebra of this generated by these measurable sets. And this is what we call finally the Motivic measure. Is this clear? Hope it's clear. It's just this construction. Okay, now that we have a measure, we can integrate with respect to it. So the idea now is to and in particular, we can finally define the second of the objects here that we're missing, which are Igusa zeta functions. Igusa zeta functions are defined as a certain parametric integral So we consider the arc space, which is our measure space.
So what is
Yeah. What is what?
B? B?
B is just the Boolean algebra of all these measurable sets, and to redefine a measure. That's
Can you read the CK inside XK finite?
what? CK in fact?
What is CK?
CK is here.
Yeah.
It's a finite union of Zariski locally closed subset. Other questions? Okay. This is just notations for actually following series. Now I'm going to tell you what is what. Okay.
Could you read the formula?
Yeah, I'm coming. Okay, so we have an integral with respect to this measure on the arc space. This L is just the motive of the line. L to the minus S, this S is just a formal parameter. So basically think of it this as a variable. You can also write T literally. And this is the order function of Z. We need it. Okay. The other function really just takes, arcs of the ambient space and basically pulls them back on Z. This is just a shift defining Z, and checks his valuation, like t-adic valuation. And if you, since this function here is locally constant, if you open up the definition of this integral, it's really just a series over the level sets of this function here. Of course, you need to measure them with respect to this measure, and then you have, this is the value that your variable takes, not the variable that this function here takes. So you have like a t to the k.
So what happens if the arc is all containing Z?
Thank you. That's something that I always skip. Actually, of course, if the arc is containing Z, it explodes. You get to an infinite. But one can prove that the measure of this subset here in Z infinite is actually 0. So you usually remove it. The correct definition is removing this. But since it's measure 0, you can forget about removing it as well. Other questions on this definition? This is the type of integral we work with. And really here the idea is that one has the order function of the variety we're interested in studying, and basically we try to understand also the singularity type at some point by checking the behavior of the arcs of this nice and smooth ambient space, what happens when you put them back on Z. Okay, and I think this is everything I needed to tell you on Motivic integration. Are there any other questions on this? Okay.
So you want your Motivic class of C here in K0 war and not in this M hat.
I mean, it's fine. It's just to define this limit here that you need. It's just to define this to give this limit. And actually, since this will come later, but since we have X is this smooth space, you don't even need this limit. Because if A is of this shape, so the pre-image of for a certain K, this actually collapses to, sorry, A, so it's CK. And this one. So you're actually, you really are here. Okay. So towards this connection, the first result we need is the following. This is just a proposition that will help us later. One can consider the following map. Oh no, before I need to tell you where this map lives. Basically, we need to redefine the correspondent of that JK rec in this Motivic language. So we consider this set as 0K of Z. Close the embeddings of this in Z. Okay, so this is basically a special type of K-jets of Z. If you want maybe to understand better what's going on in the really defined case, these maps really correspond just to this type of maps. Z. Subjective. KT. Such that is 0. And the image. Here. As it's in the kernel. Okay. So this is really, if you consider, if you think of this as parameterizations, like determined by the images that you have in here that determine these maps, it's basically just smooth curves that start at 0. This is why they're useful for curvilinear schemes, which are schemes that lie on smooth curves. And indeed, we now I tell you what's going on. Fiber. Okay. So we have these jets, this particular type of jets. We have our curvilinear schemes. Already from that quotient, we see that there should be some relationship, and indeed is this one. If given these jets here, we consider like the scheme theoretic image. This correspondence here is actually at Zariski locally trivial fibration with a very explicit fibers, just gem times AK minus 2. But the important part is that having that Zariski locally trivial fibration, we can really say something about the Motivic classes of this. Because then what we have is this. that's curvilinear schemes times just the Motivic class of the fiber, which is just that thing. And here, side note, this type of result, not exactly, but can also be obtained by the work of Gergely here already, because if we have this correspondence, we can already say that the Motivic class of the Hilbert scheme, of the curvilinear schemes, are the Motivic class of this Motivic classes of these quotients. One just needs to understand a bit better the action, in particular check that it is free, and this group then is special, and this comes automatically, almost automatically also from there. Okay. So with this proposition here now, we can finally use it to say something about Igusa zeta functions. Because you saw that jets are the building blocks of this measure. So we just need to consider a slightly smaller integration space. And we consider the generating function. This is for K, of course, the generating function of the Motivic classes of curvilinear schemes. And what we have is that the Igusa zeta function of Z, just on this smaller space, doesn't matter. Here in the definition, you simply cap with A, if you want A. Is related in a very neat way to the generating series. Shift, but then we finally have this. Okay. This is the type of relationship we have finally. The Igusa function of Z here, and the generating series of its curvilinear schemes. And the idea, I want to just give you an idea of the proof of this result, but basically it really just uses this. If we can consider Sk, the set of arcs in A, because now we don't integrate over the full x infinity, such that the order of these arcs is bigger or equal than K. Here is in the definition, one usually works with the strict equality, so really the order equal to K, but these are usually hard to measure. It's easier to measure these level sets with actually one as inequalities. And indeed, what also happens here is that the measure of this Sk, it really just comes from this and the definition of Motivic measure. It's actually just equal to that. That's the fiber which is there. Okay. So So this is what I was telling you at the very beginning. We express the Motivic measure of some sets in terms of Hilbert schemes. And then one simply plugs in this measure in the definition of Igusa function. And now it's just some over this case. Here we just need to take the differences of this of these sets to have exact equality in the order of the arcs. So again, one can see what happens. Are there any questions on this? Just understanding the measures. Okay. So now that we have this relationship, we can finally say something about the Motivic classes of these curvilinear schemes. That is the goal that we actually started with. And in particular, one very nice application is understanding them in terms of the not only of the singularities of Z, but of the resolution, really on the resolution, which is something that usually trying to understand how Hilbert schemes behave with respect to the resolution of the variety that you have underneath is very complicated. But the Igusa functions behave super well with respect to the embedded resolutions. So, I just recall the type of resolution that we work with. I will just modify. We really work with embedded resolution a la Ironaka, with a small additional condition. So it's a resolution of the pair X and Z, but simultaneously also of the pair X and 0, because we want to keep track of how 0 behaves under the resolution. I mean, just blow up 0 and then you keep resolving. And here we're interested in some numerical sets that somehow describe the eventual singularity that Z has in 0. And here we define an I. These are just the components of the exceptional divisor, and I keep track separately of the strict transform of Z. Okay, here, and I is just a multiplicity. See? Basically, it's just you just pull back the sheaf of Z to Y. For P, a smooth point of a divisor UI. Then we're interested in and these are called usually multiplicities. We're also interested in log discrepancies, which is another set of multiplicities. This time it's just of the relative.
Can
yeah?
you read the formula for Ni?
Yeah, it's the multiplicity at P of the sheaf defining Z pulled back on Y, which is the resolution space. Just pull it back on Y. For P, a smooth point of the divisor of I. Here for the new i's, it's the same. It's just with the relative canonical. And then for Mi, it's the same. Another set of multiplicities, this time for 0.
Have we been assuming that the singularity of Z is isolated? No.
No, here you don't
We
need
don't
it.
assume it. Okay.
You will need it later if you want to say something about topology. But here, no. Okay, yeah, well, this set of multiplicities might be strange looking, but they're really useful to compute these integrals. But I think I don't want to tell you anything on how to compute these integrals. I can fit here. Okay. And what we have is that using these numbers, we can describe this series of curvilinear schemes that we have in the upper board in terms of the resolution in the following way. So, can I fit? Let's see. There is an initial term that is in degree 1, so it's not particularly interesting. What's interesting is this second part here. Now I will read the formula as soon as I finish writing it. I am almost done. I promise. Okay. Okay, so we consider the set of divisors of order 1. The order was this last multiplicity. And why is that? If we keep track of how 0 behaves, you can think of it as keeping track of the valuation, how the valuation behaves. So this resembles the fact that we're working with like smooth arcs and jets. And here we have this big formula for the generating series here in terms of what? You see, we have the other two sets of multiplicities and log discrepancies here appearing as exponents in this formula, and the Motivic classes of basically these divisors of order 1, where we remove the strict transform and we take interior again, the smooth part, or the same divisors of order 1 where we intersect them with the strict. This is actually just a bunch of points in the case of curves. And it's a P1 with false in the case of curves. But so the important part here is that we have these Motivic classes and we can really express them in terms of the resolution of singularities of Z.
Could you clarify what you mean by interior? You mean that you use the interior of the I throughout?
The interior of?
EI.
Yeah, I mean, basically one follows this notation. For a JS subset of I is the full set of divisors. So now you consider all the intersection in the interior.
Okay, no.
It's just from this you remove what's left. This is just the case.
I don't see any index with a set here.
What? Here. I-ness.
Yes, but there isn't an E with the...
Yeah, it's just one. It's a very small set of indices. It's just one.
I feel like it's sometimes in these formulas in this subject we see covers of those guys. Does that not, like finite covers of those complements, do those not show up here?
No.
They don't.
I have no idea if they do. Doing something else, but I don't know. Here they don't. Okay. Is this clear? The index part is really with just one divisor.
I can ask more questions.
Yeah, of course. Are there any other questions on these formulas? What? I actually have enough time to tell you what happens in the case of curves, and maybe it clarifies as well what happens with divisors. Let's start with the output. Because I mentioned as well plane curves at the very beginning. And here I really want to give you the example of the cusp. So we take the regular cusp, E2. And if one considers its resolution, we get this. This is the strict transform. Then we have the first divisor. Here I follow the notation ni, nu I, mi. So we have 3, 2, and 1. Here in E2 we have, no, this is smaller, so this is 1. It's the same. So we have 2, 1, 1. And this is the last divisor. This is the resolution 3 that we have. We have a divisor of order 2. So it means that we don't need it, because it doesn't appear in that formula. It is excluded from the set. So in particular, we will also not see the strict transform because it intersects only this divisor that we just killed. So we're really left, we're working with E1 and E2. And I mean, here in this case, E1, you take the divisor. Following that notation, you remove everything else, basically, of the resolution. In particular, here it means that you remove just this point of intersection. So it is AP1 minus that intersection point. And the same goes on here. And here one can compute this integral. And there are many ways to compute it. One can be indeed that formula, or directly trying to study it. And this is result that one should get times minus 1 plus L. You see that just the numbers of these two divisors appear. And from this, following that relationship, for example, one can see that C here 2 is just a P1. C3 is actually just an A1. And C here K is actually empty starting from 4. But you see, these are just the 2 degrees that appear in that formula. Instead, the rest is empty. The generating series stops at degree 3. And this example is representative of 2 things that happen in the case of plane curves. Since we have plane curves, the resolutions are very easy because divisors are really just P1s, where we add or remove a bunch of points, as you can see here in the example. So what follows are actually these two corollaries. The first one is that these, okay, we consider these Motivic classes. We saw them, really think of them here. We want to study them. What we obtain from that formula, but really writing down explicitly these classes that we have here, which will be in particular here, the result is just the number of intersection points of these divisors with the strict transform. And here is actually, this is P1, where we remove the intersection points with the strict, as well as the other divisors. So that is a L plus 1, like motivically. This is an L plus 1 minus some numbers. This is some numbers. So what follows directly just from there is that these classes are actually polynomials in L. And in particular, since we work with plane curves, where we know that the algebraic geometry side, so really the resolution side, is equivalent to the topological side, these polynomials also need to be a topological invariant, really of the so as you asked me, really in the isolated case where you can really say link of that singularity, you can use it here to say eventually something more about these polynomials. But this is good. I mean, we created also some curve invariants, different curve invariants.
Can you just,
yeah?
Okay, I guess you're saying that for k greater than or equal to 4, this curvilinear function
Yeah.
scheme is empty.
Is the second thing here.
That's what you're going to tell me.
Is the second corollary. Because it is again from this theorem. That first corollary was like you obtain it out. You take this series, you think a bit more what are these Motivic classes, you realize that they're just L plus minus some numbers, okay? But then actually, you see in the example there already that the strict transform doesn't intersect divisors of order 1. And this is not a coincidence. You can actually prove that strict transforms of curves never intersect divisors of order 1. So what happens? What happens is that this side here of this formula collapses, because this will always be 0. Because you have AI intersected with the strict, that is 0 points. So you have a finite number of contributions, actually, just the divisors of order 1. Does this make sense?
Well, from the formula, it makes sense. It's just surprising to me. I mean,
This dies, this lives, but you have a finite number of divisors, especially of order 1, not that many sometimes. So from the top degree that you have in that polynomial, you obtain that K0 of curves, plane curve, is 0 for the threshold is given by the divisor, by the divisors. So check this. When you arrive at the very last divisor of order 1, you stop, because that polynomial as well stops.
So what if C had been smooth to begin with?
Okay, if C is smooth.
Then-
Thank you. Thank you very much. That's no smooth branches, otherwise this is false. Would be strange for the Hilbert scheme entirely empty. So here, this is the only assumption that you have on your curve. You can even take multi-branch things, take them as strange as you like.
But the series would contain stuff. And so I guess what I'm confused about is like what happens if you take a big curvilinear subscheme on, say, the normalization, and you try and take its image down into, where did it go?
It's wrong. It's not an inclusion. It's not injected when you push it forward.
Ah. Okay.
So for the first corollary, is it known that the invariant is only dependent on the link instead of the algebraic structure of the curve singularity?
This, topological invariant here is really like if you want the Puceau pairs, the iterated torus knot that you have. So I don't think you take into account any other structure. But maybe I'm wrong.
Okay.
You can ask me later. Ask me later what you mean, because I don't know. I don't know how to answer you. Maybe. Okay. Actually, this is it. This is everything I wanted to tell you. Thank you.
Thank you.
Any more questions? Fine.
How, once you go, say, past curves, is it easier to do hypersurfaces?
Easier to do what?
Like compute this, do you get something similar if you work, say, with something which is purely a hypersurface in, say, A3?
I don't know.
You didn't, it's something which
No,
might
I do
come up down the line.
examples mainly with curves because of the
No.
ORS conjectures. Here you can say something as soon as you know the resolution. Of course, as soon as you move away from curves, the divisors can be strange, but at least you have this type of relationship. But it's a good question, I don't know.
Thank you.
Any more questions?
Are there parts of the Hilbert scheme where you, for some examples?
I mean, that is what I'm thinking of, also partially with Gergely. Very briefly. Gently with Gergely, what we are trying to do to understand is the following. Like, if you remember at the beginning, I told you that Silk K, it is given to you by some Greg. I follow his notation. Right. It is this quotient. In his papers on tautological integrals by monomial Hilbert schemes, basically you can define other sets of components of the Hilbert schemes. If you fix lambda partition, you take lambda jets, whatever they are, and you have this, again, this quotient construction with some jets. So of course it's natural to try and use these jets now that are slightly different to construct some integral of that sort. Of course the integration changes because you don't work on your classic arcs and jets. So this is one direction, and I mean the other direction that I'm working on, which is more or less related, that you asked me, where you fix. This is just for, this is in general, this is just for curves. When you consider like the stratum where you fix the minimal number of generators of your ideals. You don't do this, but instead of working with jets, you can try and use arcs directly to create some sort of correspondent of this map that actually is still here. But here you will have arcs of some sort, and here you will have KR0. And then you try and study these maps to see if that can tell you something for the integration part. So it's slightly different. This is more similar to this.
Any other questions? If not, let's thank Ilaria again.